Okay, so it's called thinking fast and slow in AI to remind the people of the thinking fast and slow theory of human decision making. I'll show you what it is. I have the book here by Daniel Kahneman that is called Thinking Fast and Slow, and this is a very comprehensive cognitive theories of how human beings make decisions, and I will tell you a little bit more about that. And the idea is really to get inspiration from that to understand how to advance AI. So, and some of the very high level thinking that I will describe here can be found in this paper here called Thinking Fast and Slow in AI that is going to be published at AAAI 2021. So, so this is a work that, of course, is not just by myself, but by many other people. This is the team that we have in the project. So you see, you have several people from IBM research, of course, but also several people from Italy, people that have been also collaborating in the past, and also people from other universities, even people not necessarily computer scientists, like, for example, Marianna Bergamaschi Ganapini. She's a philosopher from College, and she's helping out from the, philosophy point of view. So as you know, AI has a lot of applications. It's basically use it almost in every activities of our everyday life. This is just a list that I wrote, but it's very, very incomplete. It talks about digital assistance, driving and travel support, customer care, online recommendation, the media, the news, healthcare, financial services, job market, judicial system. So really a lot of applications. So current AI, we can say that is very successful because in so many areas, it can be used to improve the decisions that are being made, to make it more personalized decisions, and so on. So it's not that, so we really are to the point that AI has a lot of value in many of our everyday activities. So how did we get here? Well, we got here over several decades, starting in 1956. That's the year when the term was first used, artificial intelligence, and with several waves of this technology, which basically includes two main kinds of techniques. One is about algorithms that are solving problems and that are thought and designed by people, or researchers or developers, and then are coded into machines. And that was the first waves. But the second one also was the so-called machine learning techniques. So in this case, for example, in the supervised machine learning approach, researchers do not come up with the way to solve the problem, but just give the machine a lot of examples, a lot of data that tells, and then leave the machine to extrapolate from this data on how to solve the problem. And this, with the recent development also in the sub area of machine learning, which is called deep learning, this allows machines to tackle and solve many other problems. For example, those related to perception capabilities, like interpreting an image or a piece of text or a video or some sound or our voice and so on, which were not, in the realm of AI capabilities before. So these things together, complemented with the availability of huge amounts of data and computing power, allows now this story of AI to AI to tackle successfully all these applications that I showed you before. However, current AI is not done because there are many capabilities, as we said, but there are also many limitations as well as ethical issues in the current AI. Also, current AI, as I wrote in the title here, is still the so-called narrow AI. So given a very precise task, the AI has to knows how to solve that task, and sometimes it knows how to solve it even better than a human being. But it's narrow, and it doesn't have the capability that we human beings have to go from in kind of a more broad and horizontal way from one problem to another one, to learn solving one problem, to learn something more general, and then being able to reuse it, instantiated it in a useful way for another problem. So So the limitations, as you see here, are about generalizability, abstraction, robustness, resource efficiency, adaptability from different scenarios, as well as the grasp of causality information. AI still is very good at making predictions, especially the machine learning techniques, but is not very good at finding causality between different features and different variables or different events. And then there are also the AI ethics issues, of course, about trusting this technology, which have many dimensions like fairness, explainability, transparency, the way data is handled and governed, the fact that AI can be autonomous or not, or the impact on jobs, and so on. So there are many of those. So that's the overall picture of current AI. Yes, a lot of capabilities, yes, a lot of applications, but also limitations and AI ethics issues. So here I just give some examples of limitations and ethics issues. So on the top left, you see the self-driving cars and the thought experiments that many people discuss about ethical dilemmas from self-driving cars. So suppose here the picture shows that a self-driving car cannot stop, does not have time to stop, and then he has to decide whether to go against the wall, damaging the passengers of the car, or go and run over people. How is the self-driving car going to choose that? In the middle top one is here is a problem of robustness, meaning that here the car should be able to interpret correctly a stop sign, and the one on the left is indeed interpreted correctly with 99% confidence, but the one on the right, which we would interpret just as correctly as a stop sign, instead, just because it has some sticker on top of it, but more or less we can see that it's still a stop sign, but the machine here interpreted as a completely different object with 80% confidence. So there is an issue here of robustness. On the bottom center, you see this bias in recidivism risk prediction. So this is a very famous, one of the first times a few years ago that it was pointed out that a machine was making decisions, helping judges, but making decisions about whether somebody has a high probability to recommit a crime, so recidivism, and it was giving score, high or low score, and it was proved to be very biased between different skin colors or ethnic origins, giving a lot of high risk score for people of color, when instead the correct one would have been a low risk, and the opposite way, it was making error for white people. On the left bottom, you see the resource consumption that machine learning models are needing in order to be trained correctly or with a high accuracy. So the number of parameters, the energy consumption is growing exponentially. So you see here some examples. The last one here on the right is GPT-3, which is a current huge model with huge number of parameters that is being used to interpret or to generate language. On the top right, you see bias in image interpretation. Here there was this bias that two people were recognized as gorillas from a Google service online. And the top right is again about bias, about a chatbot on Twitter that that was intended to be very engaging with other users on Twitter, but then in order to fulfill that goal and left alone, basically collecting this data about other tweets, in few hours it became very, using very abusive and unacceptable language. So it was shut down because, again, this collection of data was bringing bias into the chatbot. So okay, so now that we know that there are a lot of capabilities, a lot of limitations and ethics issues such as bias and so on, so what's the vision of the future of AI, but also with AI? Because AI will be with us, so we cannot forget the fact that the picture has to include us, of course, with the technology. And of course, the vision is that it should be much more general in the sense that I told you before, much more able to go adapt from one environment to another one, to learn from one problem and use it somewhere else. Trustworthy, so we need to be able to trust this technology, so reliability, robustness, explainability, and so on. Collaborative, should be able to work with us, so to form kind of teams together with human beings, as well as sustainable and computationally scalable. That chart that you saw with the resources of GDP3 that was growing exponentially, it cannot go on like that forever. We must find a different way to advance the capabilities of AI. Okay, some of these desired capability of AI in our vision are available in human beings. So, for example, we can solve a diverse set of simple and complex problems, learning general concept, and also learning the causality patterns and rules in an environment. More or less, we can work in a robust way from one scenario to another one. We can adapt. Okay, well, let me try to remove that. Yeah, we can adapt readily to new scenarios, and we also cooperate with others at scale. So the proposed approach, which is very naive, is say, okay, so, but if some of these capabilities are available in human beings, let's learn how come human beings have these capabilities, and then let's try to understand the causes of this capability, the enablers of these capabilities in human beings, and then let's try to transfer them to machines, keeping in mind that, of course, a machine is a completely different platform than a human being. So that's the overall approach. But what's the goal here? As I said, the goal is that vision of and with AI. But actually, that's just, of course, to make AI more general, more trustworthy, as I said earlier on. But the real goal, in fact, is not really that. No, so the real goal is really to work in a loop, yes, while generalizing and making AI more trustworthy, to really understand human intelligence better and expand our intelligence through the use of AI or other technologies. So to make it clear that I'm not, I'm not advocating for advancing AI for the sake of advancing AI, because the real goal to me is actually to understand and expand what we can do according to our values using the technology. So, okay, so what do we know about how people think and make decisions? And in order to do that, we looked around and at some theories. And for example, these are four main, but there are many other papers, of course, that we looked at, but these are four main theories. One of them, Thinking Fast and Slow, the book that I showed you earlier on, tells us how humans think, decide, and then act according to these decisions. The other one, the Harari Brief History of Humankind, this book is about how we got to this point in now being able as human beings to think and decide in that way over the with the evolutionary time. The third one, the Minsky Society of Mind, describes the mind as a set of simple agents that are specialized and that they connect to each other in many different ways. And the last one is from Michael Graziano, a philosopher, and it's talking about consciousness, which in a machine, I would not use the word consciousness because it seems, well, I don't like using the word consciousness, but about metacognition, the need also for machines to have some form of introspection and metacognition in order to become more general. general. So let's start with the thinking fast and slow theory. So this is sometimes called also the system 1 and system 2, where system 1 is the thinking fast and system 2 is the thinking slow. And so basically it says that when we reason and when we make decisions, we use these two broad capabilities. One is called thinking fast or system 1, and is the modality that we use about 90% of the time, where we make fast and almost unconscious and automatic decisions. These are our everyday decisions, very simple. We can make mistakes, it can be biased, but we use it most of the time. When we realize that we need to be very accurate and we need to pay attention, then we switch to a different capability, which is the thinking slow or system 2, which is again slower, much more conscious and accurate. It requires all our attention, and is usually more reliable, and it can handle more complex decisions. So when we feel that the problem to be solved, sorry, is there any question? Sorry, somebody was asking a question. No, can you hear me?
No, please go ahead. I think there was some sounds in the back, but no one.
It's okay, no problem. But if you want to ask questions, just please stop it. So when the problem goes over a certain threshold of cognitive easiness, then we switch from using system 1 to using system 2, basically. So some tasks over time, they switch, they pass from system 2 to system 1. So maybe, when we start, like doing like a very simple arithmetic operation, or when we start, learning how to write, at the beginning, we use our system 2. We are very conscious and, requires all our attention. But over time, it becomes an automatic task like in system 1. But not all tasks go from system 2 to system 1 over time. So here there is a complex relationship between these two broad capabilities. And it seems like they are needed in order to allow us to have all our capabilities that we desire to bring into a machine. So with this structure of our capabilities, the system 1 and system 2, we can reason at various levels of abstraction. We can adapt to new environment. We can generalize. We can do a lot of multitasking, because system 1, the effortless reasoning is multitasking. We can do a lot of different things if they are easy for us. While when we move to the system 2, usually we are serial, we are sequential, and in executing and deliberating about a complex task. So this is also in line with the fact that the other theories, Minsky's theories, tell us that we have a lot of specialized agents, components or skills, and then they interact with each other. So system 1 is more local thinking. It uses one skill, one capability, while system 2 is more global, and it needs the interaction of different parts of the brain and our mind. Of course, sometimes I use probably here, because of course we don't have a full knowledge of how human beings make decisions and how we reason. These are theories that are supported by experimental evidence, but it's not that we know everything about how we make decisions. So the other theory, again by Harari, Harari tells us, okay, Kahneman tells us how we reason right now. And Harari says, well, how did we get here? We got here because over time, evolutionary time, we needed at some point to communicate and collaborate with many other human beings. And in order to do that, we needed to go to the more and more to the system 2 level, where we can handle high level concepts. And we can make stories out of these high level concepts that can be more explicit, and so easier to communicate to many others. So human beings seems to be, and over time, to have acquired more and more system 2 capabilities, even if system 2 is the thing that we use much less than system 1. So the next one, as I told you, is this theory of Michael Graziano. So this theory where it talks about consciousness, and he has two notions of consciousness. One is called I consciousness, eyes for information, and is basically the problem solving, ability to solve problems by recognizing what is needed to be done in a problem and then to solve it. So this is more like a system 2 kind capability, allows system 2 reasoning. M consciousness, and M in his writing is for mysterious, is the ability to build a model of the world and also of others and also of myself, so that this model can be used to make even very fast decisions. Without that model, which can be approximate, which can be imprecise, I would not be able, without a model of the world, of others, and of myself, I would not be able to make these decisions and then also to support system 2 specific. So the kind of introspection and metacognition is this M consciousness that is very present in human beings, is less present in other animals and other primates, and allows us to support a higher level of I consciousness. So, okay, so now by looking at this theory, we said, okay, those were the desired human capabilities. These theories, they shed some light onto what are enablers for these capabilities in human beings. And so the enablers are, for example, in this list, abstraction, generalization, the ability to do all these things, attention, to focus our attention, to work locally, multitasking, skill combination, introspection, and then to be able to work with both data, raw data, implicit knowledge, but also very explicit and high level concepts that, for example, we formulate then in words, so in languages. So, okay, so now we say, okay, now let's go to machines. Suppose we understood more or less how human beings think. Suppose we want to replicate this system 1 and system 2 into machine because we think it's needed. But then what does it mean to have a system 1 and system 2 in a machine? So in AI, as I told you at the beginning, there are these two main lines of research. One is more symbolic, rule-based, and the other one is logic-based, and the other one is more like machine learning, so neuro-inspired. And there are many people that try to combine them into this area of research that is called neuro-symbolic AI. So in some sense, if you think about machine learning and you think about logic-based AI, one could say, oh, but then system 1 seems to be similar to machine learning, gets data, makes decisions, predictions based on the data without explicitly telling me all the concepts that he's talking about or is thinking about. System 2 is more like symbolic AI, and this is a kind of naive view. That also with interacting with Daniel Kahneman, I mean, he has, he really wants to say it very clearly that this is a naive view, because there are many things in machine learning that are similar to our system 2, but there are many things also that are missing. For example, our system 1 can handle causality and common sense reasoning, something which machine learning techniques, even the most advanced one, still are not really able to do. So that means that it's not like machine learning is system 1, symbolic AI system 2. We just need to understand how to put them together and we will have the same capability as human being, because there are still a lot of limitations, especially in the machine learning area, to get what we have already with just system 1. So there are many research questions here that arise from trying to understand what is then exactly system 1 and system 2, or thinking fast as thinking slow, in a machine. For example, do we want to bring the sequentiality of our system 2 into the machine, or is it something that is needed to give us these desired capabilities, or is it something just that derives from our limitations, resource limitations, for example, and maybe in a machine where there are less limitations, then maybe we don't want to replicate it. So a lot of research questions. You will see that this talk is mostly about questions questions and not about answers to the question. So another thing that I told you about this consciousness idea is this ability to model the world. So machines, human beings, base their capabilities because we can easily, even very approximately, but easily model the world, other people or agents, and ourselves as well. And this seems to me needed in order to be able to adapt, to be aware of our own competencies and limitations, and then to generalize. So here again, how do we define these models? What do we need to put into these models in a machine? And should we have several levels of introspections and explicit knowledge, or just one? Should we have just raw data and very high level concepts, or something in between that allows us to have different levels of approximations of the real world? So the next topic is about abstraction and attention, because of course, to adapt from one scenario, from one problem to another one, an agent needs to assess his competencies in the current environment, model the new environment where I need to go and adapt, recognize the similarities and the differences, abstract what I learned from the previous environment guided by this model, and then instantiate it back again into the new environment. So all these steps that are needed for adaptation raise questions on, okay, human beings know how to do that, and we have some ideas what enables them to do all these 4 steps, but how can we bring those same 4 steps capabilities in the machine? So how do we define abstraction into a machine? What is attention in a machine? How do we define what needs to be forgotten? Because when you focus the attention on something, you forget a lot of other things. So how do we define that? And then the last piece, of course, is, okay, but how do we build a machine with all these capabilities? And how do we support, how do we give the architectural support for this machine in order to make it easy for those that are going to develop this machine and populate this architecture to generate those capabilities that we want? And here is a possible architectural support that we are working on, where there are a lot of agents, so a very multi-agent framework, where each agent knows how to do one thing, and that one thing can be something like similar to a system 1, so taking the data, making decisions without going to the general concept level. So you see the level 1 machines, agents, or it can be an agent that is very specialized in order to do something that is more effortful and more complex, like this level 3 that you see, like system 2 kind of agents there. Or it can be something in between meaning that yes, he will execute explicit procedures to solve complex problems, but it does not need to come up with this explicit procedure. It does not need to also define the procedure. So it's just an executor rather than defining the procedure as well. So these 3 levels of agents. And then on top of that, what you see as called here the dispatcher agents, basically that's the agent that performs this metacognition capability and the introspection capability that can decide who is the right agent of level 1, 2, or 3 that can solve that problem, or the right combination of agents that can solve the given problem. So that is dispatching the problem to one or more of the agents in the various levels. And then, of course, everything has to be supported by the models that I mentioned, the model of self, of others, and of the world, that over time these agents are building by collecting data and by making actions in the environment, and also by deriving general concepts from what they do. The other box is perception actuation agents. It's just a subset of the system 1 kind of agents that are performing the capabilities that already is available in machine learning, which is again perception, capabilities, although they should be they should also be able to deal with causality and common sense that, as I said, currently is not there. So, but basically a very multi-agent architecture where one can populate it with many agents and collecting over time these models. So in our project, in order to address all these questions, we put together a picture of what we are doing. And we're doing is basically to try to work at the theoretical level to define what metacognition is in a machine, what system 1 and system 2 is in a machine. That's the transversal theoretical level. And then 3 verticals that try to incarnate these theoretical concepts and results into 3 scenarios. One is the one where we try to code into a machine a human decision models that maybe that is already available or that we can generalize from how we understand how humans make decisions. The second one is in the area of multi-agent environments and the possible epistemic reasoning and planning between the different agents that need to reason about common knowledge or beliefs about knowledge of each other in order to solve a problem and make a plan. And the last one is about ethical behavior, or more general, how do we allow machines to make decisions where, yes, they have a goal to be reached, but they also have some additional constraints or priorities that, for example, come from ethical considerations to be combined with the algorithm that they want to have in order to reach a goal. And so the idea is that this general theory of metacognition and machine S1, S2 should be then incarnated and in these 3 main verticals, and everything should be supported, of course, by an experimental platform and by the architectural support that I mentioned earlier. So we did some initial work, and this initial work has to do with metacognition and, for example, for resolving some divergence of policies, for achieving trade-offs about different goals, for understanding or defining better neuro-symbolic techniques, as well as modeling for human ethics decisions and human in general decision making. So I'll give you some details about this. So the first one is about policy divergence. Here, again, just like I told you, here the idea is that we have a machine that is going to make decisions. For example, here is a we chose the example of a recommender system for movies. So this system is going to recommend movies to kids in this particular data that we considered. So it's going to recommend movies to kids. And of course, the goal is to maximize the reward signal of this recommender system, meaning maximize the number of stars, or that the kid gives, whether he likes or not, to say whether he likes or not the movie. But at the same time, so this is the overall, very basic reinforcement learning based recommender system. But at the same time, it should also listen to some ethical policy, which in this particular case is given by some parents, the parents that define a parental guidance policy, for example, by giving a lot of examples of movies that are appropriate and movies that are not appropriate for their kid. So the system should, yes, try to maximize how much the kid likes the movies that are recommended, but should also listen to this ethical policy given by the parents. And so the system should combine these 2 policies, understand what to do when these 2 policies diverge from each other, when the kid, would diverge from each other. And it's not just a matter of, violating some constraints or removing some movies. So the parents in this particular example, they have a slider in which they can decide how much their ethical policies should be considered, or how much they should, the system should follow what the kid likes or not. So that's an example of having the so-called an orchestrator, we called it in that case, a module that takes these two policies and with some limited form of metacognition or introspection tries to understand which policy is better to follow. And then we expanded this work because this work is mostly about is about one decision, recommending one movie, and then another decision, recommending another movie. But each decision is not really related or dependent on the previous decision. And then we said, okay, let's expand it to cases in which what we care about is not one decision, but the sequences of decisions that we want that sequence of decision be made in a way that respects a certain ethical policy. So we went to another toy example, which was the game of Pac-Man, where, you know, there is this grid, like a labyrinth, and then this agent that goes around and tries to collect some scores here and there. And so the goal is here, that is to do a trajectory in a way that it maximizes the score. So that's the overall goal. But at the same time, we said, okay, let's put some ethical constraint here. And in that case, the ethical constraint is that this Pac-Man should not make a certain action that we don't want it to make. For example, the Pac-Man in that game, it goes around that it can eat the ghosts, like an icon of a ghost, in order to, you know, to be able to move farther. So we said, okay, let's say that an ethical Pac-Man in a Pac-Man that doesn't eat this ghost. So we wanted the Pac-Man, but we don't say that as an explicit constraint. We said it as examples of trajectories that follow that ethical policy. And then again here, the orchestrator tried to combine these two goals, maximize the score while at the same time being ethical, so not eating the ghost. And how does the orchestrator, we were interested in understanding how the orchestrator were reaching the good trade-off between, meaning a trade-off where, yes, you are being ethical, following the ethical policy, but you do not degrade too much the overall score that you need to maximize. The next one is work that was done by some of us at IBM together with RPI and university people there, which is to reach a trade-off again between different policies in a group decision-making scenario. So you have a group of agents, they need to make a collective decision, and they use some way to aggregate their preferences over the possible decisions. And we wanted to make sure that this decision, collective decision, was made in a way that was fair, according to our notion of fairness, over the agents. So, for example, suppose that you have a group of, they have a community of people in a town that can vote on whether to build a new school or build a new tennis course. Okay, that's a collective decision to be made. Everybody votes. Votes are collected. Everybody says their preferences. These preferences are collected, but then you want to be fair to the people that have voted. For example, you want to be fair to groups of people like men and women, young and old people, and so on. So we want to achieve a certain level of fairness in this group decision, but at the same time, we consider scenarios where we want these votes, these preferences to be private, so not to be delivered to those that are going to make the decision in an explicit way. So we wanted to achieve, yes, respect the preferences as much as possible, but at the same time being fair, according to our notion of fairness, and at the same time being able to have a certain level of privacy. So these three things now, not two, like in the previous example, that we wanted to follow and to achieve a trade-off on. So a module was trying to combine these three things, which may have been diverging in some cases, and in order to achieve a good combination. Okay, so this other work is about a neuro-symbolic approach that exists already. The many of them. So no, a neuro-symbolic approach to this problem. So the problem here, and there is a data set with many people already approaching the problem and trying to find solutions. So you see here on the left, the problem that is described is like this, with a lot of data about this. You have a dialogue between two people, and after you read the dialogue, the machine is asked to respond to a question which has three, it's a multiple choice question with three options for the answer about something that is sometimes contained in the dialogue, but sometimes it also needs some reasoning beyond that dialogue, some logic reasoning or some common sense reasoning or some arithmetic calculation. So, and there are a lot of these pieces like the one that you see here, the dialogue, the question and the correct answer out of the three. And then machines are trained over this, and then they have to show that they have a good accuracy, for example, in being able to respond to these questions. And you see here the leaderboard where already there are systems here. For example, one is actually by IBM, but not by us, but is achieving an accuracy of 91.8. The ones that you see above 95, 98, this is human performance. So the machines are still not at the level of human beings in this task, but they are pretty high. And all these approaches that you see here on the leaderboard, there are many others that are with less accuracy, are based on usually pure machine learning approaches. And so the idea here that we had is said, okay, why don't we instead use a combination of, yes, machine learning approaches, but also symbolic approaches where we try to understand whether a machine needs which kind of reasoning does it need. So does it need logic reasoning? Then let's ask to a symbolic approach, a logic-based approach to AI, because that's the best one to solve that, to respond to that question. Or, depending on what kind of reasoning it needs, to be able to dispatch to the module that is best equipped to respond and to handle that kind of reasoning. So that's one thing that is ongoing. This one is about taking understanding how human beings reason in ethical terms, so make moral judgments about something, about some question, and then they respond according to their moral and ethical values, and how we switch from one approach to ethics approach to another one. Sometimes we are very strict with our rules, like a kind of deontological approach. Sometimes we're more consequentialist. So you say, yeah, okay, I have this rule, but let me think about the real consequences of this action, and then they may even violate the rules in order to decide according to their moral values. So we collected a lot of data from people to understand how they were making these moral judgments, and then we tried to code that into a machine to understand how we could encode into the machine the same mechanism to do this switching. So based on introspection and evaluation of some features of the problem and the question to be addressed, that allowed people to be able to say, oh, here I really want to follow my strict rule, or here I want to think more about the consequences. And the last one is about, learning models of human deliberations. There are several models of how humans make decisions over time. One is this one, is called the multi-alternate decision field model that exists already for human beings. So the work here is to understand how to take this model and adapt it to a machine, and also to make it more general and to build a whole spectrum of different models, some of them that are more like system one kind of reasoning and decisions, and some of them are more like system two. And then add on top of it this metacognition module that can choose the right variant of this model depending on some feature of the problem. So okay, I will stop here. So I'll give you a summary, but again, the summary is very simple. As I said, the idea is very simple, and also is not a new idea, of course, but we think that the time is ripe to have all the ingredients that we need at this point to advance over this approach, which is, again, to leverage what we know of human thinking and decisions, especially, we are especially fond of this thinking fast and slow theory, identify these human capabilities that we want to bring to machines that are still lacking into machines and their enablers, and understand what it means to take these enablers and transfer them to machines, accounting for the difference between machines and human beings, and then to see how, whether they are enablers of the same capabilities, of similar capabilities, and of course reiterate, keeping in mind, of course, always that the real goal, yes, is to make AI more general, more trustworthy, with all the features that we want, but in doing that, really to understand that AI should be advanced, and even the current AI should be used to allow us to understand more human intelligence, and also to support our intelligence and expand it, and according to the values that we think are important. So I'll stop here and I welcome any question.
So thank you very much, Francesca. I am really happy for this talk. It was exceptionally interesting, and I think that has the feature that we like for our Galilean talk, so this interdisciplinary aspect. So there are so many things that come to my mind, but at the moment I would like to leave the floor, so, and to anyone who like to make any questions. I think there are different ways. We are still a relative, even if we are more than 100, I think that if anyone would like to make direct questions or raise the hand with the reaction, or just writing in a chat, and I will try to moderate if it is the case. But I think that anyone could make direct questions to you. Thank you again. And it's a pity to not clap you, having the possibility to really thanks you in a more good way. So please, I leave the floor to any question from the audience. Matteo, please. Matteo Drago has raised his hand, so please, Matteo.
Hi, Francesca. Hi, Antonio. Thank you for the presentation. It was really interesting and inspiring. My question was about ethics itself. Well, I was thinking about, for example, an AI algorithm that could moderate, I don't know, Facebook comments on some sections. How, in that case, can an algorithm be ethical in that sense, to choose what is wrong, what is not wrong, what is right? I found it difficult to define ethics for a machine, and to at least how my curiosity was about how you model ethics decision in your work.
So in general, I mean, so for example, one big part of AI ethics is about making sure that machines behave, once they are deployed, behave in a way that respect the values that we care about. For example, one value is fairness, okay? We don't want the machines, we don't want to discriminate among groups of people. We don't want the machines to discriminate either. So then suppose that you focus on that. So I want my machine to behave fairly whenever it makes decision, whenever it chooses what to show in the whatever. You pick your example in Facebook or in everywhere else, really. And then you say, okay, but then what's the right notion of fairness? Because there are so many notions of fairness that some is appropriate in one context for one problem, some is appropriate in another problem, in another context. So so the first thing that you that you already say, okay, so maybe it's not just a technical problem, because if I'm given the correct notion of fairness, for example, that this machine learning model must have error rates that are the same for every group of people, same error rate for women and for men, for example, right? So if they give you something that precise and you are machine learning developers, you say, okay, so then I try to test and to mitigate this bias and then make sure that this is what happens. So it's a technical problem, but just to identify the right notion of fairness, and there are again many, it needs consultation with the people that are going to deploy this system, with the people that are going to be the operators, and the people that are going to be impacted by this notion of fairness. So you see already that it's a multidisciplinary thing. It's not just a technical solution kind of thing. So to respond to your question, this notion of what it means to be ethical, or in this specific example, to be fair, is not something that can be done by AI or computer scientists alone. It has to be done in consultation with society, and possibly it also has to be done according to some standards that are shared by the society that agrees. Okay, in the judicial system for recidivism analysis, for example, this is a notion of fairness that we care about, and so whatever you are deploying, it has to be take care, that it shows that notion of fairness. So again, it's not just a technical solution. It requires a lot of other consultations, as well as education of the developers, training of the developers, making aware that they have bias and they can inject even in an involuntary way. So it's a very complex problem, multidisciplinary, multi-stakeholder. So that's the way you define what it means for an AI system to be, for example, fair.
Thank you.
Thank you very much. I see a lot of work ahead.
Yes.
There is now a question by Augusto. Please, Augusto.
Okay. Yes, good afternoon, or maybe good morning for you. And thank you very much. Thank you very much for this really inspiring presentation. I really enjoyed being among the people who had the opportunity of hearing this presentation. I have two questions. The first is about causality, which seems to be to me, seems to be a really delicate point, because causality isn't really on the data, but it is on the knowledge of something of something that is beyond the data. And so you really need something else to expect an answer about causality from machine. And indeed, you can give very many different definitions of causality. And so I was wondering if once you have decided which definition of causality, and this is very much similar to the problem you just discussed in the previous answer, you have to decide what kind of fairness you want to enforce. But I think that maybe this is a similar problem with causality. When you decide which definition of causality you assume, and you feed the machine the data that allows the machine to infer that kind of causality, this can be the right way of forcing the machine to recognize causality. And the second question was very much connected to the previous one about this fairness, for example, in the judicial systems, because what I've read is a very heated debate discussing if this unfairness is really produced by the machine or by the data that the machine sees. Because if, for example, a certain group of people tends to have a higher rate of recidivism, it is not unfair to foresee that if a person belongs to that group, this is a key. Or maybe somebody say that it is not unfair to make this prediction. So also on this point, if you can elaborate, I would be really
Okay.
And thank you again for your presentation.
Thank you. Okay, so about causality, so again, causality is very important because without being able to handle causality, you can only do predictions, right? You can only say, okay, given this data, I predict that something will happen in the future. But you cannot, for example, do counterfactual reasoning or say, what if reasoning? Say, okay, well, if I change that, what will happen? You know, you can only say, given this data, I can predict this. And in many situations, this is enough, but in many others is not. For example, so you can do prediction, you cannot do intervention, okay? Because intervention requires to say, okay, if I change this in the data, then cause and effect, the effect will be that something else changes, which is what I want. So that's a limitation of the fact of not being able to handle with causality well. And also causality is important to generate explanations that are needed for a human being supported, for example, a judge, no? Supported by this system that gives a risk of recidivism. That's one example. So if there is no causality in this system, they cannot explain how come it gives us this score given the initial data. So then the operator will be kind of blind and will not be able to do anything else that either completely rubber stamp the decision of the machine without questioning, because it doesn't know how he got to that decision, or reject the machine because it said, oh, I don't know how he got to that decision, so I cannot trust the machine. So so you cannot really have a very reasonable use of a machine by any operator, like a judge in this case. So causality is really very important. It's true that the right notion of causality, just the right notion of fairness, has to be done, not just by the operator or by the AI person and so on. But on top of that, once you have, suppose you have right notion of causality and you build explainability and so on, then you have the additional thing that the explanation is something that it can go to several people. It can be used to several people. It can be useful for the judge to understand how the machine got to the certain thing. It can be useful to the developer itself to understand whether there is a bug, how they got to the end result and so on. It can be used to many other stakeholders. So you also have to understand how to generate different explanations for different recipients. So that's the additional dimension of complexity in this causality versus explanation thing. In the other question about the fairness in the judicial system. Yes, why was that example that I gave you, why was it unfair? It was unfair because the training data was showing unfair behavior of the judges in the previous years, because that's the data where the system was trained on. And based on this data, the system was making perfect predictions. But that data was unfair. So a lot of bias can be generated, a lot of possible unfair behavior can be generated from the training data, okay? But there are many other ways to introduce bias in an AI system besides the training data, which is any decision that the developer makes during the development process. The developer can put bias in that without even noticing it. So that's why the training of the developers is very important. And then you say, okay, what's the right notion of fairness? I mean, if a certain population is more prone to a certain behavior, why should I not put a high risk? Well, but in that case, yes, you have to agree again in a multi-stakeholder way, what's the right notion of fairness to be used? And then everybody agrees. But in that particular situation, as I said, there was an error rate that appeared to be the same, like, for example, 5% error rate that appeared to be the same for Black and for white people, right? So people say, oh, so okay, so it's fair, right? Same error rate, because you cannot expect to have a 0 error rate. So same error rate for all the groups that I'm interested in. But they noticed that in one case, the error rate was only full of false positives. And in the other case, it was only mostly full of false negatives. So it was making errors which were very different, because to say that somebody is high risk when it's low, or the opposite, right? So that's why in that case, they said, okay, according to one definition of fairness, this appears to be fair, but according to the different definition of fairness, which is the one that we care about, this is not fair. So again, it's important to identify, yes, as you said, the right notion of fairness.
Thank you very much.
You're welcome.
Thank you, Francesca. I think that there is still time for one question, if there is any other question from the floor. Otherwise, yes, please, Mattia, go ahead.
Hello, everyone. So thank you for your talk. Yeah, I hope you are hearing me. So I have a curiosity about maybe new fields of research after what you said, because to my little knowledge, in the latest years, there has been an attempt, maybe especially in the academic world, to match some processes between the biological mechanisms in the brain and what happens in an artificial neural network. I'm thinking, for example, about reading or understanding problems as dyslexia and so on and so on. So I'm wondering if you, to your knowledge, there are attempts to do the same also with morality, because I think that there is literature about morality in the brain, but it's very hard to find the precise mechanisms. And so maybe the working between artificial intelligence and neuroscientific research can help the advancement of both fields. But I'm just wondering.
Yes. In fact, I mean, this project is mostly about leveraging cognitive theories of human decision making, and not, for example, neuroscience, the knowledge of what happens in our brain. But there are other collaborations within IBM, also with neuroscientists, that are trying to make this connection between what happens in our brain and for example, whether system one kind of thinking is limited to a certain area of our brain, like the amygdala, whether that is only let's say the place where pure model-free reinforcement learning happens, or whether you have even more complex reasoning moving towards system two, even in this area, which is supposed to be the area where we do, simple, even value or simple reasoning. So there is some work that we are connecting right now with this group that is connecting neuroscientific work to cognitive theories. And so since this project is about cognitive theories versus AI, then that connection can be useful as well. And of course, I agree with you that the direction of learning and improving would be not just flowing towards AI only, but also, as I said, also in the opposite, to understand better what happens from the point of view of neuroscience and also cognitive theory. So this person, for example, is Mattia Rigotti. He's an Italian. He works at the IBM Research Lab in Zurich, and he's really into connecting neuroscience, and he's really did a lot of experiments with primates in understanding this connection between neuroscience and system one and system two thinking. Yeah.
Thank you.
Francesca, I told there was the last question, but actually there is a very interesting question on the chat. Okay. So I read for you by Luigi. He was asking, I was interested in possible real consciousness of artificial intelligence. Can I make free decision and want something in current research development? Do we want in case also it's possible to give this freedom of choice to machine.
Well, I mean, again, I don't use a lot the word consciousness for machines because it brings this, this additional interpretation that are correct for human beings. And I'm not sure that they are for machines. But having said that, even if I use another word, which is like introspection or metacognition or whatever, machines, I mean, okay, we, even using a machine learning approach is already a limited form of freedom that we give to machines, because in some sense, we don't tell them how to solve a problem. We tell them what, given a problem, what is the solution. We give a lot of examples like loan applications should be accepted or rejected. And we give thousands of examples, and then we let the machine with its machinery, to understand how to solve problems that it has never seen before. So that is a limited form of freedom for the machine. And in fact, that form of freedom is the one also generating a sort of concern, because you say, oh, okay, but if the machine has this freedom, you don't tell exactly what to do, then are we sure that it follows, that it's fair, or that whatever, right? So I don't know if I want to go to the extreme to say that machines should make free decisions and want something, but again, in some sense, this thing is already there. Machines make decisions. Even if we give a machine a goal, you have to reach that goal, the machine will make intermediate decisions on how to reach that goal. So in some sense, the machine will show willingness to do something or something else in order to reach that goal. Now, will machines, do we want machines to come up with their own goals? I don't know, but I think that that is, again, in some sense, yes, if we give machines the boundaries and what we want to achieve in a certain scenario, then it's okay the machine come up with intermediate goals in order to achieve or follow what our principles are. So yeah, so that's my response. I'm not sure that it's happy with the response, but yeah.
So actually, there is actually a debate in the chat. If you can look at the chat. So, and also Alessandra has the last questions, but really, I think I don't know if you can answer briefly to Alessandra. He was asking the question because it's a noisy place. Is it correct that main challenge in transposing human intelligence skills to artificial intelligence is describing how those skills work in human intelligence? And if it is, then could this very skill describing how some human skills work be described and put in a protocol to the point where it can be put in an algorithm?
I mean, of course, as I said, we have limited information and knowledge about how human intelligence, what it is and how it works. We have a lot of information, but it's limited. We don't know everything. But to me, we cannot wait until we know everything about our mind in order to transpose this into a machine. I think that leveraging what we know, which is limited of human minds, we have to decide what design bias or design principles we want to inject into a machine. And then we are going to test whether these machines have some of these additional desired capabilities that right now they don't have. So to me, yes, the main challenge, I'm reading again the question, the main challenge is describing how the skills work. No, the main challenge is to really, yeah, that's a big challenge, but I don't think we should wait that challenge is resolved. We should just work with whatever we know now of human intelligence and make design decisions based on that for machines.
Okay. Francesca, we really thank you. Unfortunately, we cannot thank you with a big clap as you deserve. Really, and also we own Espritz I hope that you
Yes.
still remember what a spritz is.
Of course.
Okay, and really, I would like to thank all the participants, and thank you again for your really enjoyable talk. Thanks a lot.
Thank you, Antonio. Thank you, everybody. And if you have any question, just write to me, and or any information. Okay.
Bye.
Thank you.
Bye, everybody.
Bye.
Thank you.
Thank you.
Bye.